Hello and welcome back to the course on statistics. Today we're talking about standard deviation. Very interesting topic ahead. So let's clarify what standard deviation is once and for all so that we never ever have to worry about this again. All right, so we stopped over here when we talked about continuous and discrete, or discrete and continuous variables, and then we talked about discrete and continuous distributions, and we established, which is very important, that distributions are actually functions attached to, in our case, the columns or the variables. So they're a descriptor of our data rather than some sort of graph. A graph, in this case, a discrete chart or a continuous or the probability density function here, they're just auxiliary elements. They assist our understanding of the distribution and visualizing them. But in essence, you don't need a graph for the distribution to exist. Distribution exists independent of the graph. So with that in mind, let's move on. Let's just clear the chart, clear the area here, and we're going to talk about height, just for, to mix it up and just to make it like for illustrative purposes, going to be a convenient variable for us to work with. So here we've got 5 variables. 5 values in this data set, 5 rows. As we saw previously, it's actually a larger data set. We just trimmed it down. But for the purposes of today's tutorial, let's imagine that that is all we have, that we only have 5 rows in this data set, and that's it. That's the whole data set. In that case, let's write out our 5 rows over here, or 5 values of height. So we have 5 people. It's a very small bank. There's only 5 people who are customers of this bank. You can count them on one hand, and that's how tall they are in inches: 61.2 inches, 62 inches, 65 inches, 70.4 inches, 70.9 inches. So we want to find some parameters about our population. This is a population because we only have 5 people. It's not a sample, and we'll talk about samples populations further down in the course. But this is not a sample. This is a population because that's all the people we have in the bank. So we want to find out some parameters about this population. For example, what is the mean of their height? What is the average of their height? Well, the mean of their height is calculated as you add all their heights up and you divide by 5. And that gives you 65.92. That's going to be the mean, or that is the mean of the height of all of the customers of this bank. Now let's talk about the variance. So variance, what is the variance? Variance is a measure of spread of your data. So you know what the mean is. So we know the mean is 65.92, which is somewhere in the middle. So there you can see 65.1, 65.92 is somewhere here. And the question is, how spread out is your data? Because it could be very close. We could get 65.92 if we had all of them here, like 65.1, 65.2, 65.3, and 2 of them here, like 70, 70.4 and 70.5, or something like that, or 70.3, 70.2, something like that. We would get 65.92. Or in this case, they're a bit more spread out, all the way to 61 to 70.9. Or they could be even more spread out. We could still get the same mean sitting over here, but they could be all the way to 40 inches and all the way to what is 2 meters, 6 foot something. I'm not that good at converting these, but let's say up to 80 inches. So between you could have the same mean, but your data could be spread out way further. It could be all the way from 40 to 80 inches, or more or less. So this on its own doesn't tell us everything. It tells us a bit, but it doesn't tell us a lot, that much about the data. It just tells us one thing, it tells us the mean, but we don't know the spread. For example, we don't know the spread of this data. So that's why we want to introduce a new metric, which will help us understand, okay, so we know the mean. How are our observations spread out around this mean? Are they very close together, or are they quite sparse? Are they quite far apart from this mean? And that's why we need a measure of spread. A very trivial measure of spread that we could introduce is the range. We could just say, okay, what's 70.9 maximum minus 61.2? What's maximum minus minimum? And that would give us the range. And that would be already a good measure of, or a starting measure of spread, because of spread. Because if all the values are very close to 65.9 or 0.92, then the range will be low. If the values are spread out far away, then the range will be high. But that only talks about the maximum and the minimum. That's what if we have an outlier? It doesn't tell us anything about the ones in between. So we'll know the mean, which is over here. We'll know the minimum, the maximum, like some parameter about the minimum and maximum, but we won't know what's going on in between. And that's why we want to introduce something more robust. And that's why we're introducing variance. So variance is introduced as, again, an average. But an average of what? Well, let's start by experimenting. Let's see what we can come up with together. Let's say we take, so we already have the mean. So let's say, and we know it's sitting somewhere over there. Let's take this value, this starting first value, and we calculate the distance between this value and the mean. It's going to be calculated as 61.2 minus 65.92, because that's basically the difference. Well, this is the signed difference, so it's going to be negative here. But let's just keep this calculation consistent for everybody. We're going to take this minus this. Okay, so that's pretty cool. So you're asking how far away is this value from the mean, which is sitting over here. Next one, let's add 62 minus 65.92. So again, we're asking, okay, this is the mean here, sitting somewhere here in between these two. How far away is this value from the mean? Okay, that's how far away. We add this one. Okay, how far away? That's how far. Add this one, how far away? And add this one, how far away? Okay. That's really cool. But if we add them up, the problem is it'll always add to 0. You can check that for yourself. That's just the way that the mean is calculated. Because of the way that the mean is calculated, if you plug in the formula here, or if you just perform this calculation, in this version of variance, it would always add up to 0 because these are negative over here, these are positive, and the sum is, and they balance each other out. So what can we do to this equation to make it better? Well, we could just simply take the absolute values. So instead of taking the negative here, just take the absolute. So module of this, module of this, module of all of them, and then they're positive or 0 or positive, all of them, and that means they'll definitely not add up to 0 unless they're all the same. That's not what happens in statistics. In statistics, we don't take the module. There is a metric where you use the module, but it's not commonly used. The problem with that is just the graph of the module has a kink in it, and that means things like differentiation or integration. There are going to be problems with that. With more advanced mathematics and calculus, there are going to be problems, and it's not smooth enough. Like, probably smooth is not the right word. It's just not the best approach in the long run. It might work for us here, but in all the other applications of variance that exist in all these cross disciplines, physics, mathematics, up to biology, chemistry, pretty much anywhere, the module is not going to be the best choice. So that's probably the main reason why what we go with is squared. So if we square them, we still get the benefit that they are all positive, and at the same time, we don't have those same problems as modules. So there we go. That's what variance is. So you basically calculate the distance to the mean from every single one of these. You square it. You take the average. And in mathematics, if we put this in an equation, then it looks like this. So variance equals the sum of xi minus mu, and mu is our mean over here, squared divided by n. As we discussed, this is a measure of spread of our data. And it's fair to say that because now we're calculating how far in this calculation each variable is contributing. The distance from the mean for each variable is contributing. So if the data is spread around your mean, very tightly packed around your mean, then this will be low. The variance will be low. If your data is spread out far away from your mean, then this will be high. It will have a high variance, meaning it'll have a high, the spread of your data is high. So in our case, if you calculate it, 16.64. And now we're going to introduce a new concept, standard deviation, which you've definitely heard about before. Standard deviation is basically the square root of your variance. And in our case, it's equal to 4.08. Standard deviation is what we're going to be working with mostly when talking about distributions and statistics for data, but sometimes you will still hear about variance. Some tools use variance, some methods use variance, some equations are only valid for variance, and so on. So it's good to remember about both of them, but also standard deviation. It's also good to know that, let's say if this is height in inches, then your mean is in inches, but here you can see you're squared, so your variance is in squared inches, which is not that useful in terms of a measure of spread. That's why standard deviation is better, because it'll be you got inches squared here, and then you got your square root. So these are inches again. So you can actually add the standard deviation to your mean. You can say, okay, so what's a mean plus 1 standard deviation? Okay, so in this case, mean plus 1 standard deviation equals 70, right? 69 plus, yeah. So equals 70, or mean minus 1 standard deviation equals 61.84. So you can actually work with these, operate with them, because they're in the same units. In our case, inches. You can't do the same with variance because that's squared inches. And that's why variance is used for other things. All right, and now let's change the words to their correct Greek letters. So there we go. That's mu, which is the mean. That's sigma squared, which is your variance. And that's sigma, which is your standard deviation. Well, hopefully all of that makes sense, and hopefully that's it's pretty straightforward what the standard, so what the mean is and what the standard deviation, or the variance is and standard deviation. So mean is, what is your data centered around, and your variance or standard deviation is how spread out is your data around that while it's centered, even though it's centered around this value, how spread out is it? But probably the most important question, I guess, is how do you remember the difference between the two? How do you remember that sigma squared is variance and sigma is standard deviation? Because I used to have this problem where I would look at something, I'd be like, okay, sigma squared, variance or standard deviation. I would have to think about it, and I could even get it wrong. So how do you remember which is which? Because these are obviously, if this is your first time dealing with these are new terms. The way I remember it now is sigma squared. Look at this. So I'm just going to give you a visual anchor. I'm going to give you a visual anchor, and for the rest of your life, you're going to remember what this actually, how to remember this. Okay, you ready? All right, let's look at this. So sigma, there's 1, and the V has 1 part, and sigma 2 has 2. So the first letter here has 2 parts to it, has that line, and this symbol has 2 parts to it. So that's how you can always remember. So V has 2, sigma squared is 2. So sigma squared is variance. It's just a quick tip so that you're always on your feet when you're talking about variance and standard deviation. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.